Recording now. I am going to stop my video and I'm going to share again. Can you see it now?
Yes, Foula.
Thank you so much. So as you saw from the title, it's going to be about data science over graph data. That's what I call graph-based data science. I'll describe what I mean, because actually this is not a terminology that is common to everything, so it means different things to different people. I'll discuss some of the problems that we face in data science when we see and we need to do analytics of graph-based data, some of the techniques, and then also I will give some examples where these techniques or these algorithms have been successfully applied. Okay. Oh, that doesn't move. Okay. So the outline is I'm going to first describe what I mean graphs. What are graphs and how we use graphs for data representation. As a small overview of how we perform data science of graph structured data. Then in my mind, I usually divide them into two different things, what I call the graph analysis algorithms, where we have the graph and we try to identify, to do analytics of over the graph data, compute things that are already there, but they're not, we need to compute them. For example, like what is the maximum degree of a node? And the other thing is that what I call graph-aware MLI techniques, where the first thing we do is that we identify what latent information that's not already observable in this data. And then using this latent information, we use this latent information to do the other things. And once we finish, I'll finish with a hands-on graph-based ML AI example where I'm going to do some examples of analysis and then AI problem like a link prediction, a prediction problem over graph data. Okay. So what's a graph? A graph for data science or data people is a mathematical representation that has two different things, nodes. And it usually represents an entity, a real-world entity, a computational entity, any entity that we can create, and the relationships between entities. And the entities, we call them nodes, while the relationships, we call them edges. And we represent them with this graph structure, which comes from computer science, where a node is usually a point or a circle, and an edge is a line between the two nodes that represents the relationship. And why data graphs? Well, the question should be why not data graphs? Because everything can be represented with a graph. A data graph can represent the data intuitively. They make it easier to explore the data. For example, using the graph, this graph and structure, computer science or mathematicians came up with algorithms that can explore, analyze this graph, and these algorithms can be applied in different domains. And the other thing is that many real-world examples, and we'll see some of them, are already graph structure. Okay. Yeah. So some examples of real-world data: the internet, the World Wide Web, social networks, citation networks, protein interaction networks, communication networks, a world of co-occurrence networks. That means you have a network where the nodes are words, and if the words can appear in the same sentence, this is a co-occurrence relationship, and you can represent it. Food webs, financial networks, economic networks, and knowledge graphs will become more and more ubiquitous in analytics. And an example I have here is a particular part of a social network with some people being connected through some relationships, friend relationships, work relationships, and so on and so forth. Okay, so overview of once we have this data, this graph structure, which says it's nodes that represent something, an entity, and edges that represents relationships between entities. And one thing I want to say here is that within the same graph, different entities can represent different relationships. For as I said, in the social graph, a node can represent different people. The edges can represent relationships like friendships or work relationships or going to travel relationships or writing a paper, co-authorship relationships, and so on and so forth. So having this data structure, what can we do? What kind of data science tasks we can do? A graph-based data science is a part of data science that combines querying, statistics, and graph algorithms to power ML applications by leveraging the relationships and topology of graph data. So by using these relationships that the edges expose, as well as the topology, the structure, additional information that the structure exposes, the graph exposes, we can identify more things or the same things easier. So as I said, I divide it into two different things, what I call graph analytics, and this includes queries, graph statistics algorithms, or graph analysis algorithms that answer questions like how many customers are in a marketing graph. Like, that could be like count me all the nodes which have this attribute which is called customer, or all the nodes that describe a customer entity. Are there any fraud risks in the transaction data? Like can we find subgraphs within the graph that tell us that this is a ring of a fraudulent ring? What's the most important influencer in a network? Like, can we find nodes in the social network that are very central or that they have many edges among other people? And the second part of data science is graph enhanced ML AI, where we use more advanced analytics or deep learning techniques or AI techniques or machine learning techniques in order to identify latent, that's unobservable information, for example, queries or features that are not directly observable. And once we identify them, we can use them to do more downstream tasks, like, for example, using this information, we can do different ML tasks like regression, prediction, and so forth. And so, we will touch, because it's an overview, we'll try to touch all of this. So it is going to be a little bit shallow trying to get all of them. So we'll start with graph analytics, see some examples. By the way, I just want to say something here is that both of them, they're equally important in the everyday work of our data science. Like, they're both used, although academically some of them get more focus or more attention, both of them are equally important. So, so for the first one, as we said, the graph analytics, as we said, having the data, we can have simple database style queries, like retrieve explicit patterns within a data set. Like, give me the names of George's co-authors. So there is a node that's called George. There is a structure that there is a graph that describes its co-author. So we fetch all the nodes that have a direct relationship, and this relationship is a co-authorship relationship. Compute the average salary of a company's employees. So all these are direct information that we can directly query from the graph in order to answer such questions. The other thing is graph statistics, which are usually based on local properties of graph nodes. For example, give me the graph density, could be, which is a histogram of all degree distribution, which is the histogram of all the nodes distributions. The graph density, this could be a histogram of the number of edges per node, the graph size, how many nodes you have, how many edges, and so on and so forth. Simple graph statistics that don't need a lot. You can identify by finding the nodes and getting the local properties. Like, you don't do any kind of navigation within the graph. The other one is graph algorithms, and those are algorithms that usually employ graph traversals. For example, one of them is connected components, identify all the strong connected subgraphs within the big graph. And what's a strongly connected subgraph is a subset of the nodes that each one has a relationship with each other node. Okay. Another one is community detection, partition a graph based on specific relationships. Centrality, reveal which nodes are important based on graph topology. Node similarity, identify nodes that are similar, not only based on their local characteristics, for example, some attributes that are already part of the node, but also based on what are the neighbors and the properties of their neighbors. Pathfinding, find the shortest path or most efficient path to traverse a graph. And the other one, and another one was very important, is link prediction, like having a graph where you have some of the edges, identify some of the edges, identify new edges that are not currently observed or have not been already described, but they have a big potential or probability that that these are actually real edges, that these edges exist, that this relationship that the edge describes exist. And as we some of these algorithms, we can see is that in order to identify to solve them, or they are based, some of these algorithms are based on ML techniques themselves. For example, the link prediction, which is based on some prediction techniques. Okay. Now, an overview of some of them, the connected components. As we said, the connected component is getting one graph, trying to identify all the graphs that are connected, and here connected is not strongly connected. That we say is connected means that for every node I can go to every other node with a finite number of steps. And usually these algorithms are breadth first or depth first, mean the breadth first, starting from a node, explore all the neighbors and continue recursively. And there are variations for both directed graphs and undirected graphs. Now here I haven't actually said what's this. The edges can have a direction, and which might mean something. For example, a friendship relationship is probably undirected. That means that it is the same relationship holds both sides, while directed there can be relationships that hold only in one side. For example, teacher-student. So when you have a teacher to student relationship, that's a directed edge, because the teacher, except if the student is also a teacher, of course. Now, these kinds of algorithms have been used in image processing, a lot even in entity resolution deduplication. Like entity resolution here is that you have, it's usually applied in text, and you try to identify within the text real world entities in cybersecurity and fraud detection. Before continuing, any questions so far here? No. Okay. Another of the algorithms is community detection. There are a lot of them. Examples are Louvain or label propagation, and their use cases, application is multiple, like in social networks, extracting topics from online social platforms, in criminology, identification of groups in criminal networks, in public health, discover dynamics of certain groups susceptible to an epidemic disease, customer segmentation, identify group of people that use the same financial service or they have the same buying patterns. Bioinformatics, investigating the human brain and finding hierarchical community structures within the brain's function. Basically, there are a lot and very heterogeneous. Like community detection is one of the very ubiquitous tasks using graph analytics. Okay. Node similarity, as we said, so having a graph with nodes, try to identify nodes that are similar, and that can be based on the node's own features. A node can have a feature, for example, if we are talking about person. The features can be the physical characteristics, it can be their if it is a health related, could be their electronic medical records and so on and so forth. The nodes of the features of the neighbors of that node, similar neighbors, and that's a recursive definition where the neighborhood does not need to include only direct nodes based on graph topology or any combination of the above. And use cases again is entity matching or resolution. Graphs usually are used a lot in entity resolution, and entity resolution is a very key NLP, sorry, natural language processing or text processing task, and a lot in recommendations. For example, identify customers who bought, recommend for, answer the questions, customers who brought this item also brought, and that can be extracted from knowledge graph of a big retail company, having information about customers and items. And doing this, use the node similarity to kind of answer this question. Another one is centrality, which identifies central nodes or important nodes. And the variation, there are different variations of centrality. Could be degree centrality, like nodes that have a lot of direct connections, closeness centrality, nodes that can reach other nodes with few hops, between the centrality, nodes that sit on the shortest path of lots of pairs of other nodes, and eigenvector centrality, which are nodes that are transitively connected to other important nodes. And use cases is that, as we said, social media influencers. It has been also used in fighting fraud and terrorism. And by the way, the numbers are references to the actual papers or publications or references if anybody is interested, and predicting flow traffic in flow in traffic delivery and communication systems. Okay. And the last one is pathfinding. So, and again, this is identify important paths or relevant paths or applicable paths between two nodes or from one node to all other nodes. And the algorithms there are usually known computer science algorithms like shortest path, A star, minimum sparse tree, random walks, and so on and so forth. And use cases are try to find directions between two physical locations, degrees of separation between people, travel plan, financial analysis, and graph embeddings, which we will discuss in the next slides. Okay. And before I continue on the graph awareness techniques, I'll stop a little bit to ask again if anybody has any questions. So far, everything is clear? Okay. Yeah. Now, as we said, again, I will remind what I mean by graph-aware ML AI techniques. So here is the part where we use advanced analytics or ML AI techniques in order to identify information which is not directly observable. Like the previous one, the information is there, it's observable. We only need, and we just compute it. We'll start with what is called graph kernels. Now, graph kernels can be intuitively understood as functions that quantify the similarity of pairs of graphs. So getting, say, assume that we have two graphs, for example, here G1 and G2. I can devise a kernel, which is a function that say something that the result of this function is quantifying, is giving you a number that quantifies the similarity between those two graphs. And for my example here, say that I have a kernel which is based on shortest path. I can identify what is the similarity between these pairs of graphs among those three graphs. Okay. Now, what's a graph kernel? So the idea of the graph kernel is that assume that I have two graphs, which they look, we saw how the graph is represented by nodes and edges between nodes. Now, if I have a way that like this function phi that maps every graph into a feature space. A feature space is a high dimensional space that its dimension is describing some feature of that graph. Okay. Then, and this is a metric space. Again, what it means is that I can define similarity between them. Now, if I can identify the similarity between those two graphs in that feature space, which I describe it here as a dot product, but basically it is a similarity. Then I have a good weapon, which is I mapped the graph, which is this sets of nodes and edges between nodes, to a space that I can compute. I can use my mathematical or other tools to do further computations. Now, that's where this mapping can be, although it is very advantageous, can be impossible to identify. For example, it can be a very high dimensional space. Like it could be a space of a million dimensions. And identifying this map in this function phi might be also very hard. So the kernel, what it does is that if instead of doing that, I can devise a kernel function, which the result of the, when I apply the kernel to the graph structure, I get the similarity, the value of the similarity of these two functions, then I'm done. I already gained something, because I don't need to identify this feature space, which I said it can be very hard to identify because it can be very high dimensional, or this f function can be very complicated. So if I can identify a function that I don't need to go through that, then I have gained. And of course, this new function kappa, I call here the kernel, has to be easier to compute. Okay.
Foula?
Yes.
Can I just confirm that in the similarity here, it should be G1 and G2 inside? Or
yes, G1, it's a type of, yes.
Okay. Thanks.
Yes. Because we said we measure the similarity between these two graphs. Okay.
And one more question, please. So what properties does this kernel guarantee to satisfy or try to approximate?
So we'll see some of the properties in order for these functions to be valid kernel. But the kernel, the one thing it will have to do is that to be able to give you a number, a value, and this value is the similarity. Okay, that's it. That's basically what we want to do. So we want to find a function that if I apply directly on the graph structure, then it gives me a number, that this number is the similarity that I would get if I could go through this feature space. Okay. Now,
okay.
And now going out, what are the requirements of these kernel functions? Now, a function, in order to be kernel, it has to be a positive definite in order for that to be a valid kernel function. It has to be expressive also, like it doesn't define it defines a non-trivial similarity among those two graphs. And it represents subgraph features that allow it to tell if the topology node or edge levels of the two graphs are familiar. It is applicable to a wide range of graphs, because if we need to find one kernel function for every different graph, and you saw this graph structure is so versatile, there are millions, a lot of them, infinite number of them, then they're not practical. And also it's efficient to compute, because it's if it is as complicated as going through the feature mapping, then we don't gain anything. Okay, so this the idea is that if I have the kernel function, if I can devise a kernel function that has all these properties, then I can compute this similarity, which is used in a lot of applications or other algorithms. Then I have gained not having to go through this feature space identification. Okay.
Yeah, excuse me.
Yes.
My name is Camille. I'm a PhD student in mechanical gestion and imaging. I'm not sure I understand something. The kernel, it has to be a function that uses the two graphs as argument, or you can apply it to individual graph and then compare the results.
The arguments have to be the two full graphs, yes.
Okay. Okay.
Of course, you can devise a kernel function that inside does not use the properties of the one graph, but then the value that you'll get, it's very unlikely that it describes the similarity or the difference between the graphs, right?
Okay,
if you only use information from the one graph. Okay.
Yes, I have questions.
Yes, go ahead.
Yes. I want to ask about do you have any prior information to choose the kernel function? Do we have any prior information to choose the kernel function that can represent the features, subgraph feature? That's that can generalize the subgraph in the graph.
I'm not sure I understand the question, so let me try to answer. I will see whether this is relevant. So when somebody divides a kernel function, the prior information that it has is that they work with a graph. And graph has nodes, a graph has edges, graph has paths, graphs have subgraphs. Okay, so the very what is called at the very high level, the very high level. Sometimes when somebody defines a kernel, might also give more constraints, like I'm going to work only on unidirectional kernels, or I'm going to work on graphs, or I'm going to work only on bipartite graphs. Okay, so this is, we can call a prior information. But for a kernel to be general, it wouldn't be advisable to think of specific graph, except if somebody says, "So I'm going to work on that domain. I know the features of my kernels, for example, of my graphs. They're random graphs, or they are they follow the small world assumption." So then they can define a kernel that works best optimized for that. So the prior really depends on the constraints that the person who creates the kernel will put. And then, depending on this, based on these constraints, the kernel is applicable to different kinds of graphs that will have to some level satisfy these constraints. Okay.
Yes, thank you.
Does that is this relevant? Is this what you were asking?
Yeah, I want to ask, is there any specific constraint to maybe to decrease the size, to decrease the space of kernel function? Because depend on the problem, we can have different kernel that can maybe generalize. Yeah,
that's what I said. It really depends on the person who creates the kernel. Okay, so usually in your everyday work, you'll have a library of kernels, and you say, "Oh, these are applicable," or "I'm not sure which one, so I'm going to try this and this and this and see." But this is not the person who creates the kernel. The person who creates the kernel puts their own constraints. So there are two different actors here. The one who creates the kernel puts some constraints, and the person or the actor who is using the kernel. So depending on them, there are different requirements. Like the person who's using the kernel might have specific constraints. I'd apply that on that domain, doing prediction, or applying that kernel in order to do some pattern matching. Okay.
Yeah, thank you very much.
Okay, so a kernel function now, they have been proposed, let's say, different kernel variants, but they usually, all these kernels take the form of the aggregation over metrics that describe different aspects of the graph topology. So a lot of them, and probably I would say the ones that have been more successful, well, successful mean that they have been applied also in some practical applications. They are based on local structure. So the assumption there is that two graphs are similar if they are composed of similar nodes and have similar local neighbors. That means that when I define the kernel, I look at the node, at each node, and their direct neighbors. I define a local similarity function there, and then I define an aggregate similarity over all nodes in the graph. That could be one. Then another one is another family of kernels is where they look at graph components. So they compare graphs by identifying the best possible matching of the components making up the graph. So they say, oh, two graphs are similar if their nodes are similar, if they have labels, the labels are similar, the edges, the number of edges or the relationships among different nodes are similar. There are some similar subgraphs. And the final one is kernels that are based on paths and walks, where they compare sequence of node or edge attributes encountered through graph traversal. So two graphs are similar if they have a lot of similar shortest path or a lot of similar random walks. Okay.
Excuse me, may I ask some question too?
Yes.
I'm a bit lost in labeling of the vertex.
Sorry, labeling of what? Can you repeat, because I didn't hear what you said. I stopped like
No, we must have a connection problem with Reza.
Ah, okay. So I will continue and yes, because I think I probably dropped. Okay, so let me continue a little bit. There. Okay. So can you see the slides? I'll continue seeing the slides.
Yes.
Also, I want to say something. This is a little bit kernel construction is a very hard problem, and it also what is called it has a lot of both science and art there. I'm going to define a function that takes this takes graph features, and the graph features here are nodes, paths, edges, labels between local features of the nodes, and define a function that is that describes the whole graph. Okay, so it's not easy. Very okay. Now, once we have these graph kernels, and as I said, as part of the data science, we don't usually define the kernels. There is a library of kernels. Some very smart people that work on the domain and have proposed some of them, and we usually use of some these kernels, and we see which one works is applicable or works well in the domain and the problem at hand. So applications is an ML AI. The first thing is it allows kernelized ML algorithms like SVM to work directly on graphs. So what does kernelized ML algorithms mean is that algorithms where they don't need to access directly the features of the two objects that they work on, but they only need the similarity between two features. So one of them is the SVM. So once you define a kernel on graphs, these algorithms, these ML algorithms are applicable to graphs as well, and can also be employed to learn node embeddings. As we said, it's the second time saying we are going to describe about what is node embeddings. They have also been applied in chemoinformatics, predict the toxicity of chemical molecules, in drug discovery, virtual screening, bioinformatics, protein function prediction, and in web data mining social networks for node classification and leak prediction. And now we go to the graph embeddings that we already saw twice. So in embedding in general in ML and AI is consists of representing a complex object, or an unstructured object could be text, images, graphs, with continuous vector. So we represent one object with a continuous vector. And what is a continuous vector? Is a vector of continuous numbers, usually of a reduced dimensionality. That means that the number of that constitute this vector is relatively small compared to the dimensionality of the dataset, for example, and I'll give an example of what I mean here, while keeping most of the important information about them. So for example, if I defined embeddings of words of the English language, then the dimensionality of this data set is all the words in the English language. That's big. And if I can define an embedding that, for example, can keep the most of the information, say, within 100 numbers, so I have a vector of 100 numbers, then I have reduced the dimensionality of my data set, which is the English language, to 100 numbers. That is what is the reduced dimensionality. Okay. And for example, here, I say that again on the English language, if my embeddings can keep the information, for example, can cluster royals versus how they're called, other people, so the royals closer together, or some other properties, then we kept the information that we need from that data set. Okay. So
let me ask something.
Yes.
So in this example about the English language, what is the continuity aspect?
The continuity aspect is, I'm not sure whether I understand what I said. The continuous vector is just a vector of continuous number, real numbers. That's the continuous, what we say here. So when we say a continuous vector, is a vector of real numbers. That's it. There is no continuity, other form of continuity. I didn't describe any other form of continuity here.
So
okay.
Basically from the English words that you present us here, you are going to take a vector of continuous numbers.
Yes, and actually, sorry, in this example, if we have 4 words, right? We have king, queen, man, woman. And the vector is 2 numbers because we define it in the 2-dimensional space. So we went from 4 words to 2 numbers. So yeah, go ahead now. Just wanted to, on this example, to explain what would that mean.
But the number Foula should have a meaning, right? Should represent, it's the distance that you mentioned previously, right?
So the number, no. What I said is that the vector itself should represent, should keep some important information. So for example, here in this particular example, we create a vector so that the royals and then the non-royals, the people that they are from the royal family, they're clustered together. So that's the information that we keep on this particular embedding.
Okay, I see. Thank you.
Okay, so yes, so embeddings, another term for this is representation learning. So you'll see a lot of this in both, it's basically, I was going to say AI, but it's in artificial intelligence. Now we'll go to the graph embeddings. We'll stick to the graph embeddings. So graph embeddings will be, again, an embedding, a vector, a continuous vector that somehow captures information on the graph topology, or node-to-node relationships, or some content information if the graph has contents in the form, for example, of node labels. And for graph embeddings, we usually have 2 kinds of embeddings: node embeddings and whole graph embeddings. From among the 2, the node embeddings are usually more preeminent. We see more of them because they're easier to construct, and also they have a lot of applicability. Okay, so an example here, assume that we have this graph where the colors on the nodes edges describe some relationship. For For example, it could be a social graph describing my friends or the people that, and the colors describe some information of people that have a common ideology, for example. A good embedding would be graph embedding, a vector in the 2-dimension, what we see in graph B, where the nodes that have the same ideology, they are set on the 2-dimension together, the one I have on the B graph, on the graph on the right. Okay. Let me see if yeah. So node embeddings. So in the node embeddings, each node is represented with a continuous vector. Continuous vector is a vector of continuous number of floats, and it has a fixed dimensionality. That means that it is the number of values in this vector is fixed. It could be 2, as in the previous example, 3, or so on and so forth. They are used in order to perform visualization, like the example we had before, or prediction at the node level. For example, link prediction. For example, we have a node that we know some of the edges, and we want to identify whether there are other edges that they're not already present in the graph, but they have a big probability to exist, like the relationship that describes is real. Popular techniques for this is random walk-based approaches and deep learning learning approach, where in random walk we see some examples where we use random walks in order to produce these embeddings, and then deep learning approaches we use as some form of deep learning algorithm neural network. Now, okay, so we'll use, I want to show some examples just to get an idea of how they work, and also to call out for some of these important algorithms, like somebody wants to use, they can be directly used. So one is deep walk. Having a graph, we sample a lot of random walks. That means that we start from random node, then we perform a random walk, and then we create. So this is our input. So our graph, we map the graph to a set of random walks, and then we use a skip-gram MLP network that accepts a node from the random walk as some format, some input, and to maximize the probability of predicting the neighbor nodes. And the neighbor here is if I give one node in the random walk, it can identify what was the previous node and what's the next node. Okay, or if there is no direction, just the nodes before the adjacent nodes. Okay, and once we have in the skip-gram network, MLP network is a network. MLP is a multi-layer perceptron that we described before, and a skip-gram is usually a skip-gram MLP network is a network that sees part of the input, part of the random walk, and tries to predict the masked out, the parts of the random walk that is not given to it. And once we have that, the node embedding is the output of the last hidden layer of the network. Okay. So this needs a little bit of MLP that we described before. We said before, an MLP is a neural network that has an input layer, which is the input to the graph, some number of hidden layers, and then an output layer, and the output layer is the layer that does the prediction. In this case, is the layer that tries to identify the nodes that are not given to the input. And once we have that, in order to find the embedding, we get the last layer of the network. That is, it's embedding because it is a set of perceptrons. So a perceptron is outputting a number, and this is the number that they are used in the vector representation of the embedding. It's pretty intuitive and simple, but it actually works pretty well. Now another one, which is it's a very similar variation, but it just changed a little bit the random walk to better user exploration requirements. So in the random, so basically it's the same model, but we change a little bit the input. So in order to perform a random walk, the random walk accepts two additional parameters. One is Q, which controls the likelihood to discover an undiscovered part of the graph, and P controls the likelihood to return to the previous node. So if we have large P, then the random walk will stay more local. While if I have a large Q where it tries to discover more parts of the graph, then the random walk will try to do more breadth first. Like from what I am, I'll try to explore all my neighbors before going deeper or more recursively in the graph. Okay. Any questions on these two algorithms before going on? Both of them are basically random walks. The only difference is how we create these random walks, trying to give some more strength on particular characteristics. Locality.
Sorry.
Yes, go ahead.
Sorry, yeah, I had questions in the previous slide. Can you come to previous? Okay. Yes, but this network you mentioned in the second step, it is. Is it different from the autoencoder?
Yes, it is different from. It's what we call multi-layer perceptron, and basically you can think of it as every layer is a set of perceptrons. Okay, and from one layer to the next, every perceptron has connections with every other perceptron in the next layer. That's the MLP. Okay. Now, so encoder onto, so you said the encoder onto a card. It's not exactly a different network. There is a different architecture where I use, again, dense layers, the layers that I just described. I can use because decoder is not really a specific architecture. Like I can use different building blocks to create an encoder decoder. So here the architecture that I described is very simple. Is that I have how it is called layers of dense layers of these sets of perceptrons. Okay. Now, yeah, I don't think the coder could have the same thing, like the encoder could have sets of perceptrons that each layer has a smaller number of perceptrons, and then in the encoder each layer has a larger number of perceptrons from the previous one. So that could be a decoder, yes. But that's not that's not used in deep walk, but nobody says that it couldn't be used. Okay. You can think of this that it's only using the encoder part, if that helps you.
Okay, thank you.
Mm-hmm. Okay, so just also to say about the encoder, decoder, they're usually used. The main difference is what you do is the task that you want to do, which is to recreate the input, but the input is given all as it is, while here parts of the input are hidden. And the problem that we try to solve is I'm going to predict the parts of the input. So you see, no matter what the architecture, also their prediction tasks are different.
Excuse me?
Yes.
Yes, sorry, I would like to know the node, the input of the MLP that you shown before. The nodes are represented as what? As vectors containing the concatenation of the property of the node and the edges.
Yes, just give me a continue. Actually, it's a bit different because it is say that it's not the input that you want, is the representation of the input. Okay,
Yeah.
so the representation of the input here is, I think it actually says, is one hot vector as input. So this could be for a, actually it's a little bit, I'm not actually sure. I think it depends on the implementation, but an efficient implementation is that I have a vector that you put as one. So the size of the vector is the size of the number of nodes in the graph, and you put as ones the nodes that you visit during the random walk. A more what is called a storage expensive architecture could be that for every node they have for every step of the random walk, I have a one hot encoding vector which has the size of the vector is the number of nodes in the graph, and you have a concatenation of these vectors for every node in the random walk. So it could be either of the two.
Okay, thank you.
Okay, so graph sage. So the reason I want to describe the graph sage is that contrary to contrary to previous or next algorithms that we see, is what it enables something which is called inductive learning. Let me try to explain that. So most of the algorithms that we saw so far, basically all except this one, assume that the structure of the graph, the nodes and the edges are already given, and the training and the prediction happen in one step. Okay. While the inductive is the training can happen in the first step, and then the trained model can be used what is called in a different step in the future step. Assume that I have and it can have unseen nodes. So in the inductive algorithm like graph sage, we don't need to know the nodes in advance, while in all the other algorithms, we do need to know the nodes in advance, all the nodes in advance. Like we can do link prediction, but we cannot add a new node in the graph. Okay, so is there something here? Yeah.
Sorry?
Yes.
So I have a small question about graph sage. And how we can encode an unseen node using graph sage?
Well, you don't need to encode a node. That's the idea. Is that what you need is to be able to, from this unseen node, to extract the information that you need.
Yeah. So in this,
and this happens through aggregation. We'll see. But you don't need to encode an unseen node. That's the key.
Okay, so we can say that graph sage is make node embedding, because graph sage don't present representation for each node.
I don't understand the question. I'm sorry.
So
can
graph
you
sage
rephrase it?
So I would like to know if graph sage can make node embedding.
And whether graph sage, yes, it can create nodes embeddings, yes.
Yes, and I see that node2vec and deep walk are unsupervised method, right?
They are unsupervised. It depends what you mean unsupervised vectors. For example, if you assume that the links are given and that you predict the links, then the link, if the node, like if you can find a graph that the nodes are already there, the edges are already there, and you do a link prediction, yes, that's unsupervised. But then you can also see the problem as that it's a supervised, that you need to give me the existing links.
Yes, but when we build our embedding space embedding, we don't need the labels.
Which labels? I didn't describe labels anywhere here. In the link prediction, you try to find whether there is a relationship between two nodes. So somehow you need to be able to identify the nodes. You have node IDs. Okay, and then you can say that an edge between node 1 and 2 exists. So, or it doesn't exist. So as input, you have to give which relationships exist. So then you phrase or you state your problem as a supervised problem.
Yeah, I get it. Thank you.
Okay, so, but as I said, if these are graphs that they already exist, for example, I don't know, you get a social graph, okay, and you don't need to explicitly create training data, you don't need to explicitly create edges, then yes, you can see it as an unsupervised technique. Okay. But the model itself assumes that I know these links. Okay, I need to be a little bit faster because we're getting. So for the graph sets, what I want to say, yes, which might actually answer some of the question, is that in order to be able to work with unseen nodes, the embeddings that it creates, the function that describes the what is called the embedding is an aggregate of the neighborhood. So if you can, if you can compute this aggregate, then you don't need to know how many nodes and what actual nodes exist, as far as you can compute this aggregate function. Okay. That's how it becomes an inductive method. Okay. Yeah, I'm not going to go into that. The aggregate functions could be like things like a simple average or an MLP followed by max pool. And usually it's used, what is used here is an LSTM on a random permutation of nodes in the networks. And the reason for this is because LSTM is a sequential model. So you need to have, in order for that to become permutation invariant, you need, in theory, you need a large number of permutations as input, so it will learn to learn these invariants. But in practice, what we usually do is we do a sample of random permutations as input to the LSTM. Okay. Now, before I finish, and as we said, except from node embeddings, there is also a whole graph embeddings. In this case, the entire graph is represented with a single vector. And they're usually used in order to do predictions at the graph level, or to compare or visualize graphs as examples that we saw. It's a relatively, well, I won't say good, an algorithm with a relatively stable performance is graph to vec. And a lot of techniques have been proposed in the literature. But so far, none of them we don't have a clear winner, or a winner that has large acceptability. And the reason for this, because it's such a complicated problem, of course. Okay, I am not going to go through the graph embedding. Because I want to talk a little bit of the graph neural networks. Now, another way of getting node embeddings is through graph neural networks. Now, again, graph neural network is not a specific architecture, and actually it is, there exist as many graph neural networks as papers proposing graph neural network, which is a lot. But they have some properties in common. They're usually connectionist models. And when we say connection models, it means a model that combines different models as part of its architecture. For example, a graph neural network can have MLPs, multi-layer perceptors as part of the architecture, and they try to capture relationship represented in the graphs. There is in the graph neural network, there is what is called the recurrent unit for each node in the graph, and each unit maintains stateful information, and that's the embedding of the graph that captures the properties of the related node, as well as the properties of the neighborhood of that node. Okay. And this, what is called, this recurrent unit is, as we said, the embedding, and we'll have it here as the triangle. Now, except of the embeddings that you have for every node, which is this unit, we also have for every edge an MLP that tries to learn the importance of the properties of this underlying relationship, of the relationship that describes these sets. Now, it doesn't need to be an MLP. That's where the variation starts. It can be an attention mechanism. It can be a simple aggregation. Okay. And so the neural networks, how they work is that for every node, they perform an aggregation operation on the outputs of the units that describe the edges in order to identify, in order to integrate on the unit of the node the properties or outputs of the neighborhood of the node, of the neighborhood of that node. So every node, it keeps the information of the embedding node, and then it also integrates information for the of the embeddings of the neighborhood nodes, as well as the relationship between those nodes. Okay, because we have both nodes as well as edges here. So, and both of them can describe different relationships. Okay, so that is the general concept of the neural network. So another thing, as we said, that at every node, some form of aggregation is performed in order to capture the information and integrate the information of the node through the node embeddings, the information of the neighborhood nodes through the embeddings of those nodes as well as the information of the edges that are described in the edges through the MLPs that we described. And the vector that results by taking the sum or the aggregate of all these of all the node embeddings, it represents the vector or the embedding for the whole graph. Okay, and here, as I said, a sum, it can be a sum, it can be a concatenation, another aggregate operation. That's how the graph neural network can produce both nodes, node embeddings and graph embeddings. Of course, this last point, like I create the graph embedding based on summing or concatenating or integrating the embeddings of the nodes can be applied in other algorithms as well. The advantage of the neural networks is that by construction, it has already, for the nodes embeddings, it uses information both on the node features as well as the edge relationship, the relations that are represented by the edges. Okay. Now, applications of graph neural networks in ML/AI is usually node classification and link prediction. And they have also been applied so far in different domains, in physical systems, model interaction networks, and predict future trajectories, in chemistry, in image classification, in combinatorial optimization, have some promise as alternatives to relaxation-based techniques. I would say here in optimization, that's actually a very exciting field where if somebody can define their optimization problem that they have in the form of the graph structure, they can use graph techniques like graph neural networks in order to perform the optimization task. In social graphs, we saw examples here, as well as in transportation for traffic prediction. And I think that concludes this tutorial. And at this point, I'll take any questions if you have here. I'll have a 2-minute break before we go on to a hands-on example of analytics on graph-based data. I'll stop it a little bit so I can see if there are any questions. Stop sharing.
May I ask my question again? I got disconnected when I was asking my question.
Sure, yes, I realized that. Yeah, what I said is I didn't hear what you said. Can you?
So yeah, I got disconnected. I'm sorry about it. What I want to know in definition of kernel, the labeling of the vertices, how important they are.
Ah, okay, understand. So first of all, the vertices don't need to have labels.
But that's where I have problem. Like how, like if I give you the same graph with two different labels,
there's not what you need is to have to be able to uniquely identify a node. That could be a number that identifies a node, or that could be an ID, a hash.
Yeah, but that's like labeling for me.
Yes.
So
okay.
But if I have two graphs that look very much the same, but the ID of the vertices are different. Will
okay. So in this case, the first thing you have to do is that you have to represent your graph that way. So you have to add in your nodes features that differentiate the nodes among themselves.
But what I'm asking is, if I do this, the kernel property of these two graphs with another graph can be different.
Then you have to see if there is a kernel, because that's what I said. The kernel is there are two different people. Is the people that create the kernels, the researchers, the practitioners that create kernel functions. They do spend their time creating kernel functions, and the people that use it. So if you want to use a kernel and you want specific properties, you need to go see among different kernel functions, among different papers that describe kernel functions, which one, if there is any, that you think takes into consideration the properties in the graph, in your case, the labels of the nodes, that, yes, whether there is any of them, and among them, which ones you want to try.
Okay.
The question is the same as, okay, when I have a prediction problem, which model I'm going to use? There are machine learning problems, models. There are deep learning models, different architectures of deep learning models. The question goes there.
Okay, thank you.
Sure. And yeah, I'll have only 1 minute because I just need to get a little bit of water and then I'll start. So I don't want to waste your time.
May I ask something?
Yes, go ahead.
Do you have you seen any results in whatever regards graph analysis in algorithms when dynamicity comes into the picture? For instance, the graph changes dynamically, and then you may have to compute again some of these algorithms, you know,
yes.
like.
So that's a good question. And actually, it's a hard question to do analytics on a dynamic graph. There are different ways to approach, and what I'm going to say might not be, is definitely not covering everything, but it has approaches that I have seen in papers I have used also. One is to create a universal graph that describes the whole history, like how the nodes, so you'll have either some way of unfolding the history in one graph, and you have information and you encode the time information within the graph, and then you do analytics there. So you create a huge graph that unfolds the whole thing, then you do a graph analytics there. The other one is that you define a model, like you divide your problems into part that describes the history, that is a sequential problem or some kind of a graph problem, depending how time spans, and you solve this part as one problem. Use models that identify sequence, for example, deep learning LSTM models, and then you combine this information with a graph structure a structure that describes the relationships. So again, this is a bit up a very how to say high level, because it really depends on the problem how you can divide it. most of the times, though, in practice, in problems that I've worked, we either omit the dynamicity, like the time problem, or we create an unfolded graph, like we unfold the whole history in one graph.
Mm-hmm. Okay, thank you very much.
But in the literature,
any links in this direction?
I have specific problems. Like I can think of a paper that solves a specific problem.
I see.
Yes. So
we can
that's why
discuss it offline. Okay,
yes, that's why I say like this will solve, and then in Unity comes how you represent these things.
Mm-hmm.
There is, what I can answer is that there is no model that can, there is no general purpose model that can combines the two.
Mm-hmm.
Any other questions? All these are great questions. Yeah. Because it's getting a bit late, I will actually go ahead with the example. Just give me a minute to start.
I think you may have a 1 minute break.
Yeah, that's okay. Yeah, because it is actually it's not that. I just want to. It's more of a give you an idea of things that you can do during the when you have a graph-related problem. I'm just looking to share a screen. I want to see here. Can you see my browser screen? Let me see if I can.
Yes, we can see it.
Yes. It's small. I don't know why it does. I'm actually trying. Let me stop sharing and see if I can make it larger and share again. That doesn't work. See? Yeah, there it is. Okay. Is this a little bit better? Now the fonts. Can you see?
We can see it pretty well, Foula.
Okay, so I'll start first with doing a little bit of exploratory analysis on the graph data set. So first I load the data in pandas, okay, and excuse me. The graph is what is called is a society of friends data set. It's kind of, its name is each node is a person who have some information about this people, for example, historical significance and gender, date of birth and date of death, if there is any. Okay. First of all, I'm sorry, missing one. Yes. I will load. We load the data set. Okay. So some of these people are related to some other people in the graph, and we have this information. Okay. So we create these edges here, and then one thing is we can create and visualize the graph. Okay. So you see here, the edges, as I said, are given in the data set. So yeah, we can inspect some information about what is called about particular nodes. For example, we have a node, a person called George Keith, is a male, and the birth date was 1638. So this is, as I said, is exploratory analysis. Like you get your data, you try to understand what's the contents in this graph. We can also, once we kind of understand the graph. Now, one thing I want to say here is that I visualized with a library that's called NetworkX, which is a very good library in Python for analytics on graph, but if somebody wants to do visualization, then they usually use different software for that. Okay. Example is graphics or Gephi, and there's another one that is also related there. NetworkX gives very basic visualization. We just wanted to see here what are the components, the connected components in this graph. Okay. Now we can compute some basic network statistics. For example, the density. Okay.
I have a question.
Go ahead, please.
Yeah, I wanted to know if this statistic can guide us on the type of kernel to use.
No, we don't have kernels here. Here is simple statistics.
Yeah, I mean, in general, do these statistics help us to guide on what type of kernel based on the problem we have?
Okay, I understand what. Yes, sorry, I understand. So the kernel in order to choose the kernel, you will have to choose what are. First of all, you have to understand the characteristics of your graphs, and then you want to define, approximate, when do you think that two graphs are similar? Because as we said, the kernel, the main issue that it describes or the computes is the similarity between graphs. So if, for example, two graphs for your case is similar when most of the nodes are similar, for example, most of the nodes have the same number of edges, then you're going to try to find a kernel that defines the similarity based on that characteristic. So exploratory data analysis will give you an idea of what's the content of the graph, and maybe what is a simple topology of the graph. Okay, as well, sorry, as we'll perform here some of the analytics that we saw in the first part of the slides. For example, which are central nodes, who is a very popular person here, for example.
Yeah, okay.
So yes, it's a not very dense graph. Density is a form of connectedness. We can compute shortest path between nodes. I use here two specific nodes. The shortest path is 2. That means that there are 3 people, that there's three people in the path, 1 person between those 2 people. We can compute connected components and the diameter of the largest connected component, and the diameter here is the size of the smallest path. And we can also compute the transitivity ratio, which is the transitivity ratio of all triangles over all possible triangles. And these are measurements of connectedness in the graph. Okay, and then we can see also centrality measures, like centrality measures could be, as we said, based on node degree. And here we show the top 10 nodes with the largest node degrees, with the largest edges that come out of those nodes. Other important nodes can be based on eigenvector centrality, as we described it in the slides, or between a centrality. Here again, we compute the between a centrality between all the nodes, and we sort them, and we get only the top 10 nodes. And we can also perform a community detection. One thing I want to say here is that for community detection, and then visualize them. Let me see that. So we computed some communities, and then we visualized each community with a different color. Now for community detection, the one algorithm that is usually used a lot is the Louvre. Is not part of the NetworkX. The algorithms that they have here, they tend to create a lot of small communities like what we saw here. So if this is not what you want, this is probably not a good community detection algorithm, or it might be depending on your a problem. Okay, so that's the first example, just a little bit of exploratory data analysis on a graph. Also, I want to say is that all these graphs, for this community, for example, you can identify the exact nodes. Here I just wanted to visualize it. If you actually want to see the nodes in each community, you can extract it. And as a second step, example, I want to describe an example of the ML-based graph data science, where, and I'm going to use the link prediction because I've been talking about it a lot. Like we have a graph, we know some of the links, and we try to predict the rest. Now, I'm going to use the same graph, and what I'm going to do here, let's load the graph, is visualize something. Okay, and what I'm going to do is I'm going to delete some of the edges. And if we see here, I think I have 20%. I'm going to delete 20% of those edges. Where am I? Here. Okay, so let's see. Before it was 174 edges. Now we deleted up here. Oh, sorry, am I wrong? Yes. We do the same thing. Let's do that. We deleted 34, remain 140. Okay, visualize like this. We'll compute, and how I'm going to solve the problem is I'm going to compute node embeddings on the node with the 140 edges. You see, I didn't change the number of nodes. I keep the number of nodes because I'm going to use a transductive method. Okay, so I'm going to use a node to vector for this. And the node to vector, as we said, it creates a node embeddings. Okay, so we can inspect some of these node embeddings. It takes a bit while because we are actually running the algorithm. Actually, I think it takes because it hasn't finished training it yet. So wait a little bit for this. But it doesn't take that long, like it will finish in a couple of minutes. And how I'm going to create this node embeddings is I'm going to, to predict those lists, I'm going to use the node embeddings. I'm going to define a similarity among two nodes. And the pairs of nodes that has the biggest similarity, I will rank these similarities, and I'm going to take the top n pairs of nodes, and that's the new edges that I'm going to predict. That's one way of predicting edges. Sorry for that, it's a little bit slow. Yeah, okay, so as we said, we created the embeddings. And actually, what I didn't say is that node embedding dimensionality, how much I use, this is 64. Okay, so that means that every node is now described by a vector of 64 numbers. This is the number, and this is the continuous vector that we've been discussing. Okay, so given a node, I can see which are the most similar nodes. Okay, and then I'm going to perform the link prediction with the way that I described to you. Okay. So that means that I have for every node, I will choose some anchor nodes. It could be all the nodes in the graph. I'll compute the embeddings of those nodes with all the other nodes. From the ones that I don't already know, I will compute the similarity based on a similarity measure. Usually here it could be similarity measure, it can be a dot product, or it can be a Euclidean distance. Okay, and then we'll rank the similarities, and we'll use the top k of them in order to predict that these are the new that these are probable new edges. And what I show here is that depending on what is this n, how many nodes we keep, I measure the accuracy. And here you see that if we have, if I only take the one edge, I have a 5% accuracy. I use the top k edges, the top most probable edges. I go up to 35% accuracy. And that basically concludes the example. And at this point, I'll take any additional questions if you may have. No more questions? Okay, then thank you again for being here this afternoon. I hope you learned something about graph data science, and have a good afternoon. See you next tutorial. Goodbye.
Please excuse me, are we going to have the notebooks?
Yes, they are actually already being distributed. I give the code
okay.
beforehand.
I didn't receive.
It was in the email, but they will be as part of at the site when the let me actually stop recording. I'm sorry.